Okay, we're just talking about circles. Excuse me. I asked everybody to circumscribe a triangle about a circle. So what shape is on the outside? The triangle. So again, you could do any triangle you want, but then you should have a circle on the inside. That's not bad, honestly. I'm pretty impressed.
Better than mine.
Okay, so that's pretty much it from 9-1. Was there anything that did anybody try the assignment for 9-1? Was there anything that was like super confusing or you didn't know? It wasn't bad, it was okay? Everybody's kind of all right?
Wait, was that page 30?
I have no idea. So let's move right along to 9-2, tangents. So we just spoke briefly about what they are. So if you look back at our diagram here, a tangent line would be one that intersects a circle in just one spot. So I gave the analogy of a bowling ball sitting on the floor, and that point where the bowling ball is touching the floor, that is referred to as a point of tangency. So in my diagram here, let's say I had line EF would be a tangent line, and then C would be the point of tangency. Make sense? Okay, so the first super cool thing we're going to learn about the tangent lines that's on your note sheet. If a line is tangent to a circle, then the line is, you ready for this? This is so cool. Then the line is perpendicular to the radius drawn to the point of tangency. Perpendicular to the radius drawn to the point of tangency. So, let's draw a picture of that. I have my tangent line. Sorry. I don't know why I made it so big. Okay, so here's my circle with its tangent line. A, B, and then I'll make point C the point of tangency. So, what this is telling us is that if I have a line that is tangent to a circle, you ready for this? This is so cool. All I have to do is draw in a radius. It could be a diameter, it really doesn't matter. But if I draw in a radius from the center to the point of tangency, it has to be perpendicular. Wow. So if we go back to our bowling ball analogy, the floor would obviously be horizontal, and then doesn't it make sense that a radius drawn from the center of the bowling ball straight down to that point of tangency, wouldn't that be a vertical line?
Yes.
Right? So, I mean, it doesn't always have to be horizontal and vertical, because I could just turn my paper sideways, right? And now they're not horizontal vertical anymore. The point is that if I have a line that is tangent to a circle, and I draw a radius to that point of tangency, it will always be perpendicular. Oh, that's so cool. Right? And so, of course, if I had a diameter, that wouldn't change anything. So, diameter or radius, really. Drawn to the point of tangency, 90-degree angle. Oh, golly gee whiz. Pretty cool, huh? I bet you're like, oh, I can't wait to see how we use that. Or maybe you already know, because maybe you already tried the stuff for 9-2. I don't know. Did you? Oh, geez, Louise. Okay. So, the next one, let's read the next common tangent theorem. Huh, what the heck is this? Common tangents. So, let me show you a picture of common tangents before I go ahead and finish this, because maybe you can figure out what they are. So, I'm going to have a circle, and then common tangents refer to two lines that are tangent to the same circle. right? Okay, so let's say I had tangent line there, and then I had another tangent line there. Oh, that's pretty good. So now I have 2 points of tangency. One there and one there. So let's add A, that's B, that's C. I can make these D, E. There we go. So common tangents would refer to each of these, right? They're both tangent to a common circle. Common tangents, right? Anybody want to take a guess what's true about those common tangents? Ooh, you're close.
Equally apart from?
Yeah, well, if you mean that AB is equal to AC, you're spot on.
Yeah, because the radiuses are like,
Yeah, basically what you have, right? So if I draw in the center, and so let's call this circle F, if I dropped the perpendicular to each one, because a radius drawn to a point of tangency, you're now a 90-degree angle. You're now a 90-degree angle. Isn't this looking familiar? Like we did this one time somewhere? Yes. Yes. I don't know if you recall, but when we had an angle and then we had a point on the interior of the angle, and if it was equidistant from, so imagine, you don't know this yet, right? Imagine that you don't know that those two sides are marked the same. If we had a point inside of an angle and it was equidistant from the two sides of the angle, then what was true about it? Why? You're getting there too fast. You don't know this yet. You don't know this yet. You don't know this. All you know is this right now. This is the same length as this. And you have a point inside. If you look at a big old angle DAE, and you have a point inside angle DAE that is equidistant from the sides of the angle. This? Yeah? Yes, yes. So these two triangles have, basically the theorem was that we learned way back when, was that it has to be on the angle bisector. Yeah, so, but yes, so I can get these two triangles are congruent, and that's one way that I can show for sure that AB and AC are going to be equal. Now, we already learned all that back info. All I need you to remember now is when you see a picture like this, I need you to know that these two are the same. These two. It kind of makes a funny little, like those, oh, I was thinking the dunce hat. But ice cream's probably better. Oh, but he's a dunce, so he would be sad. I don't want to be a dunce. That's such a weird word. Any hoosers. So, there's your common tangent theorem. So, let's fill it in. Common tangents are congruent when one endpoint is shared and other endpoint is tangent to same circle. Oh yeah, sorry. Okay, so the next one here says, if a line is perpendicular to the radius of a circle at the point of tangency, then, so what do you think happens in this scenario? I need a line perpendicular to the radius at a point of tangency. Well, it kind of gives itself away. by even saying the words point of tangency. They're saying in here, if I'm given this diagram and I know this to be true, I know that's a right angle, even if they didn't tell me that this line is tangent, now I know it has to be. Because only tangent lines would have a radius perpendicular to them. You get what I'm saying? So like if that was a secant line, it wouldn't necessarily be perpendicular. Follow me or no? Yeah? Okay. So if a radius is perpendicular to a line at a point of tangency, the line must be tangent to the circle. That's all it's saying. So let's fill that in. Then the line is tangent to the circle. Tangent to circle. Okay. Everybody's all right? Okay, we're doing good. So, common internal and common external tangents, I think, are best described in picture form, and then we'll put it in words if you like. So, common internal tangents, that's going to refer to, I have two circles, and a common internal tangent, let me switch colors here, would look like this. It's going to be tangent to both circles, and it's going to go kind of like that. So, I mean, you can make it long if you want. So that pink line would be referred to as a common internal tangent. So in words, we could say a line that is tangent to two circles and passes in between them. So then a common external tangent is sort of the same idea, except it doesn't pass in between them. It'd be sort of on the outside like that. So that's like if you have the floor and two bowling balls. The circles don't have to be congruent either, though. You could have like a bowling ball and a golf ball. And the floor would be a common external tangent. Does that make sense? The common internal tangent, I guess I never really noticed this, but it's really just a percent sign, isn't it? Just sort of flopped over. Ah, there you go. Oh, so, in words, common external tangent, line tangent to two circles, but does not pass between them. And then you can have such a thing as tangent circles. Oh, what fun. You ready? So, tangent circles, what do you think they are? That's pretty much it. So, it would be two circles that intersect each other, but again, it's only at one single point. Okay, so it would not be like a typical Venn diagram. Right? So we're not talking about ones like this. Oh, like that, right? That's not it. It is, so they also need to be coplanar. So let's throw that in there. Coplanar circles, tangent to same line at the same point. So when you actually look at them, it could be if I had a bowling ball, oh, that's a terrible one. Whatever. A bowling ball and then a little golf ball. And I was kind of sort of looking straight on at them. This is a terrible drawing. But I'll assume you get it. Or I could have ones that look kind of like this. That just hit right there. And then here's the line that they share. That tangent line. These are referred to as externally tangent. And these would be internally tangent. Okay, how are we doing? Let's try maybe a problem or two from this section and make sure that we know what we're talking about. So let's take a look-see-loo here. 9-2, you're supposed to do 355, or 335, sorry. We're still gonna do 9-3, 9-4, but before we move on, let's just get our ducks in a row here. Okay, so let's see. Let me ask you a couple of questions. What would you call these circles right here? Actually, I'm so glad that you said that. You raised such a good point that I forgot to mention over here. Huh? Yes. So it went back to the inscribe, circumscribe stuff, right? They have to, if you were going to inscribe, I don't know, let's say a square in a circle, right? The vertices of the square have to be on the circle. So it'd have to look like this. You could not do a circle with a square in it like that.
So then you also wouldn't do a circle on a circle because they'd be the same circle.
Correct. So I can't inscribe a circle in a circle or circumscribe either way. So yes, that's a good point that I failed to mention. So anytime you're doing inscribed or circumscribed, the vertices have to touch, or if you're doing a circle on the inside, the circle would have to be tangent to the sides. That one's worse, but you get it. So you couldn't just do a triangle and then a circle in there like that. Doesn't count. Has to be tangent to the sides. Oh, I'm glad that that came up. Okay, so any hoosers, I'm still waiting for the vocab word for these circles.
No, concentric.
Concentric circles. So those are circles that have the same center. That's your target logo or your bullseye. Those are concentric circles. Okay? What would you call these in letter E? These are internally tangent circles. Yes, yes. Whereas B would be externally tangent circles. Correct. Okay. All right, so I'm happy with all those things. And then I'm just looking at whatever we could kind of chip away at that'll have you doing less later. So 3 through 6 I wanted you to do. Oh, and the written exercises. All right, let's say we were going to do number 6 together right here. I know you can see the answers, but pretend that you can't. Okay. So RS and TU are common internal tangents to the circles. Our Z is 4.7. ZU is 7.3. Find RS and TU. How?
Congruent.
Who is?
So TZ is congruent to CU. Oh wait, no, never mind. Sorry. ZS is congruent to ZU.
Yes. Remember that? Remember the dunce? Yes, the ice cream guy. That's better. Right? So, from Z to U and from Z to S, these two are tangent to the same circle. So they're equal to each other. So this piece is also 7.3, which means that this piece, if that's 4.7, that's 4.7. Does that make sense? And now, so lo and behold, RS and TU both happen to be 12, and they just so happen to be equal to each other. How about that? We okay? So you could cross that one off your list. That was one of your homework problems. Now you have one less. Let's try. Oh, I want you to do 14. Maybe we could do 16 together, though. You could. It's blue. Ah, here it is. There you go.
Thank you.
Yep.
Is here okay?
Yep.
Thank you.
Thank you. Okay, let me just cover up the answers here, because I don't want you to see this. Eh. Okay, is everybody with me? We're going to do 16 on 337, which is this one here. Whoa. Should I give you a minute to try it without me telling you anything? Okay, try it. 16. We got answers? Maybe? So, I've drawn the diagram a little bit bigger so I can see it and mark it. Alright, so here's what they tell me. They tell me that SR is tangent to circle P and circle Q. So this thing is tangent to these two circles. So that's already a big bit of information that's going to help me somehow. Yeah.
So, how I started, I said that QR is 8.
You don't know that. In order for QR to be, if I had like R and then it was tangent to somewhere over here, QR isn't tangent to this circle. See how it's cutting through it? If you had another line from R that just grazed the side, that would also be 8. Yep.
The radius is the point of tangency, so it's perpendicular to.
Yes. They told you that SR is tangent to both of these circles. That means that that's a 90-degree angle and that's a 90-degree angle. That's a big deal.
So then you use Pythagorean theorem to get either side, which is.
Oh, yes, you could. I wasn't even thinking that. But yes, why not? Look right here. Don't you have a 3, 4, 5? So now you know QR is really 10, which means that PQ is 20. And I don't know what else you have to find. PQ, oh, PS we need.
It's 3 to 1. The ratio 3 to 1 when you use both little.
So what do you say PS is?
18.
I agree. Aren't these similar triangles, this little one and the big one? By what? Angle, angle. They both have a 90-degree angle, and they both share angle R. So I basically have two similar triangles, so she's using the scale factor. If you look at this side is 10, this side is 30. So that means that the big triangle is 3 times as big as the little. So if this is 6, that means this is 18. Oh, very nice. And what else do I have to find? ST.
So I use
ST.
it's 16.
It's got to be 16. Yes. So you could do the same thing. If this side's 8, that means this whole big side would have to be 24. So that means it would have to be 16 over there. Or you could do side splitter, right? 10 to 20. So that would have to be 8 and then 16. But if you don't put those 90-degree angles in, I don't know how you would do this. Okay. So there's that. All right. Are we doing okay? Everybody's fine? Do you need a minute before we do 9-3? I'll give you literally 1 minute. I'm actually going to stop this video.